This system is designed to implement a number of I/O sensing capabilities into a single compact motion detection system. The system detects synchronous and asynchronous stimuli using real-time operating system concepts we have learned throughout this course. The Fancy Pants contributors are
Kevin Galler,
Lucas Gramlin,
Matthew Vanderpool,
and Kelly Wachtel.
The two main components of our motion sensing system are the MC9S12 Demo NE64 board, produced by Freescale, and the ADXL335 3-axis accelerometer, produced by Analog Devices. The secondary components of our system are comprised of a 9-volt battery in conjunction with a 9-volt barrel jack connector that will supply power to the system. A miniature breadboard will be used to mount the accelerometer. Command strips will attach the various components to the board, and prototype wires will be used for the electrical connection.
Process synchronization is achieved through a reader-writer schema depending on the function of the task itself. Sensing tasks interact with the system as writers, while reporting tasks interact as readers. The calculation task interacts as both a reader and a writer. It interacts as a reader between the accelerometer sensing task and itself, and as a writer between the displaying task and itself. Inter-process communication is achieved through the message queuing system allowed by Micro-C OS2. This queue acts on a first-in, first-out basis, where writers place their messages on the queue and readers receive the messages from this queue. In this way, we have achieved process segmentation that allows the system to interact on a global scale without disrupting the function of a synchronous or asynchronous task. Another thing that we have implemented is the status flag. This allows each task to report its status to the global system without interfering with the interaction of another task. This is implemented through a status flag variable in a function that all tasks can call. Each task interacts with this status flag in strict accordance to the reader-writer schema. While every task can read the status flag and see what that is, only the task associated with that motion can set or clear its specific flag variable.
As seen in the video on this slide, the pitch and roll angles of the system are reported and displayed on the output terminal. Even while the system itself is completely inverted, the angles maintain accuracy and are simply flipped by 180 degrees.
Sensing was done by obtaining 10 X, Y, and Z samples from the accelerometer. These samples were stored using dedicated message queues. To allow for separation of the various motions, an order of precedence was implemented. Check was chosen to have the highest precedence because it was detected by using a combination of logic used to detect both click and shake. On the other hand, shake had the lowest precedence because it was the most easily detected.
The 10 values that are gathered are used to detect shake, click, and check. Shake is detected through a moving weighted average to put emphasis on the XY plane. This allows the threshold to be below 1G, resulting in more accurate readings. Click is detected through a moving average in the Z direction. This threshold is above 1G because it only uses one axis. Check is a combination of both these. When a motion is detected, the system stops sensing other motions until the reporting is finished.
As seen here in the video, when a movement is detected, it is reported on both the LEDs and the terminal output. A shake is defined as movement in the horizontal direction. A check is defined as movement in both the horizontal and vertical directions, as an ASCII check mark is drawn on the screen. A click is detected as movement in just the vertical plane. In addition to the reporting of the terminal, when a click is detected, an audible sound is output to the computer speakers.
As seen in these videos, a unique LED code is assigned to each movement. Check reports its occurrence with a bouncing pattern between the two LEDs. A click is shown by holding the LED solid for a few moments, while a shake causes the LEDs to flash, alternating rapidly. When none of these movements are detected, the system enters an idle state and uses the LEDs as a constant timer, flashing every 2 seconds.
Okay. As shown here, by using two axes for pitch and roll calculations, we are able to report the full 360-degree range of motion. Upward motion is reported between 0 and 180 degrees, while inverted motion is reported between 0 and negative 180 degrees. The accuracy of these measurements is somewhat dependent on the accuracy of the accelerometer itself. While we have verified that up to 45 degrees accuracy remains plus or minus 1 degree, for angles exceeding 50 degrees, accuracy tends to degrade. This is due to the sine-like nature of inaccuracy produced by the accelerometer itself, which inherently introduces a plus or minus 1.5 degree inaccuracy. This inaccuracy, compounded with the rounding of integer numbers for displaying, results in an inaccuracy of about 4 to 5 degrees in the max extreme angles.
The potentiometer is output to the terminal, as shown in the video to the side here. However, the potentiometer itself suffers from some minor reporting inconsistencies. Occasionally, it reports altered values when no change has actually occurred. It is likely that this is due to the vigorous motions that have occurred during the course of testing our system.
Motion detection testing was calculated by completing each motion 25 times. This resulted in 100% shake accuracy, 88% click accuracy, and 80% check accuracy.
If either switch is pressed, then it is reported by both the LEDs and the console. The switches can also be pressed simultaneously and will be reported accordingly. This project has been an invaluable learning experience for our group. It has taught us much about inter-process communication as well as process synchronization.
Furthermore, we have learned to do systems programming through the development of an application programming interface used throughout this project.
We also gained familiarity with working in a real-time operating system environment through the use of microC OS 2.
Thank you for watching, and a special thanks to Dr. Kim.